So, my name is Mark Porter. I'm General Manager of RDS for Postgres and the Postgres edition of Amazon Aurora. With me is Kevin Jernigan, Senior Product Manager in the same groups.
Hi, welcome.
And if you were at Andy's keynote yesterday, you know that we're launching a preview of Postgres Compatibility. And Kevin and I have been working together on this for a while. And even before that, Kevin and I were working together at Oracle starting in 1988, 28 years ago, on scaling databases, including Oracle RAC, two-phase commit, NoSQL, and all those other things. Well, we both think that the combination of the Postgres database engine with the AWS cloud is amazing, and we're excited to tell you about it, and it's a privilege to work on it. So let's start. What are we going to talk about today? We're going to go through and we're going to tell you how we built, why we built Amazon Aurora. We're going to tell you how it's doing and why we think Postgres compatibility is important. Then we're going to cover how Amazon Aurora literally re-envisions the database. It re-envisions durability, availability, and performance. And Kevin is going to show you some pretty fun performance slides. They'll actually be numbers and graphs. Then we're going to have a surprise guest speaker to introduce you to a new feature of Amazon RDS, Performance Insights. And finally, we'll talk about what our next features are. And as Andy Jassy likes to say, giddy up. Traditional databases like Oracle, SQL Server, MySQL, and yes, even community version of Postgres are hard to scale. They're designed as multiple layers of functionality in a single monolithic software stack. They run slow together. They don't scale independently. The different layers don't scale independently, and they fail together. They're very tightly coupled, and I like to say, and I've worked on these for, like I said, 28 years, they perform at the LPD, or the lowest performance denominator, and that's not what you want. In fact, one of the reasons NoSQL has been so popular is that people need to scale out various layers of this and not scale out the other layers. However, at the same time, nobody said they didn't want transactions. So let's see what we can do and what people have done in the past to fix those problems. Well, first off, people started with sharding, where you shard your keys across the cluster. Well, number one, this is very application dependent. Number two, you lose the ability to join your data sets. And frankly, about the only good thing you can say about sharding is that it's not one of the other two solutions up here. Second, people focused on shared nothing or two-phase commit. And without going very deep into that, the problem with it is that performance was abysmal. And except for some very well-tuned data sets and transaction loads, no one uses it today at all. Third, people decided to get really smart and put an immense amount of science into putting the buffer cache together and putting the storage layer together. And they tried to make it simple to use, but frankly, it hasn't happened to date. Kevin and I both worked on Oracle RAC version 6, and it's the kind of thing where people are going around where it's complex to deploy, incredibly expensive, and typical RAC installations have a bunch of highly paid DBAs dancing around them, chanting reconfiguration spells. There's nothing you can do about it. And that's not anything wrong with Oracle RAC. It's the fact that fundamentally you're addressing the problem wrong. You're actually making it more complex rather than simpler. So what would you do if you were going to write a database today? You'd break apart the stack, and you'd build something that can scale out, something that's self-healing, and something that leverages a bunch of distributed services. So we did that. And we're going to tell you today about how we applied a service-oriented architecture to the database. And so the very first thing we did is we took the logging and storage tiers out, and we made them multi-tenant, self-healing, and distributed. And because we're in AWS, we depended on services like Amazon S3, Simple Workflow. And then you'd let it be managed in the same way all your other databases are managed, using Amazon RDS. We knew all of this from our days writing databases at Oracle and from our days managing databases at Amazon, big, true, mission-critical enterprise databases. So way back in 2012, a bunch of folks, led by Anurag Gupta and his team, Anurag's an old buddy of mine from Oracle, decided to go do it. And so they built Amazon Aurora. Now, how many of you use Amazon Aurora today? We need to improve that. As a result of all that work, Anurag and his team produced Amazon Aurora, a cloud-optimized relational database. Amazon Aurora provides performance and durability by implementing a fully distributed and self-healing storage system. It provides availability by using the elasticity and the management capabilities of the cloud. Amazon Aurora launched in 2014, and it's been a pretty exciting ride since then. So Kevin is going to tell you a little bit from the product side about how Amazon Aurora is doing in the marketplace. Kevin, here you go.
Thanks, Mark. So Mark told you a little bit about why we built Amazon Aurora, but how's it doing with our customers? Well, from the time it went GA in July of last year, Amazon Aurora has become the fastest growing service in AWS history, by far, actually. And it's got a lot of competition for that title because we have a bunch of other amazing products with fast growth rates like Amazon Redshift, Elasticache, and even RDS for Postgres itself. And here's what some of our customers have to say about their experiences with Amazon Aurora. At Funny or Die, they've seen major performance benefits. GoGuardian loves the low replica lag. Zynga, who's been in production for more than 8 months with Amazon Aurora, is excited about performance without operational overhead. And Alfresco can process documents 10 times faster with Amazon Aurora. And we have many more customer stories about the tremendous success they're having with Aurora. When they hear about the performance and reliability of Amazon Aurora, customers assume it's a premium priced product. However, Aurora has allowed many customers to actually reduce their bill by reducing the number or size of instances they need, by not having to pre-provision for future storage peaks, or by taking advantage of the fact that adding an Aurora read replica does not change their storage cost, thanks to the shared storage layer. One example is Safe.com. They've lowered their bill by about 40% by switching from a sharded MySQL implementation to a single Aurora instance. They were able to do this because that single Aurora instance provides enough performance that they no longer need to shard into separate instances to do that sharding scale-out picture that Mark showed you. Another example is Double Down Interactive, a gaming company. They lowered their bill by about 2/3 while also achieving better latencies. Most of their queries now run faster and lower CPU utilization at the same time. So what's next? I think you already know what's next. We've announced this. In 2014, we launched Amazon Aurora with MySQL compatibility, and now we're adding Postgres compatibility. We're going to make Amazon Aurora even better for our customers with Postgres compatibility. This means that customers can now take both existing MySQL and Postgres applications and run them in Amazon Aurora, getting all of those benefits of higher performance, higher availability, and lower costs. So at Amazon, we always start with the customer. In this case, customers who have relational database requirements. And as I've already shown you, we have seen high and growing customer demand for Amazon Aurora with MySQL compatibility. They like the performance, durability, availability, and compatibility with their existing MySQL applications and skill sets. So why add Postgres? Well, at the same time that we launched Amazon Aurora with MySQL compatibility from the day we launched, customers have been asking for the same capabilities, the same enterprise database capabilities, but with Postgres compatibility. They want all that durability, availability, fast read replicas, performance improvements, but with Postgres. Now, they aren't saying they want to move off of MySQL. They like the MySQL compatible edition of Aurora, just a lot of customers also want Postgres compatibility with those same characteristics. So when we drill down with customers in more detail about their relational database requirements with respect to Postgres compatibility, they tell us about several scenarios. They want to migrate existing Postgres applications from on-premises or from EC2, or they want to migrate from Amazon RDS for Postgres due to database size limitations or performance scalability requirements, or they want to migrate from Oracle or SQL Server platforms to help lower costs, or they want to build new applications that leverage the combination of Postgres with Amazon Aurora. But let's drill down a little bit more on why our customers are interested in Postgres. Well, Postgres is an open source project that started more than 20 years ago as a follow-on to the Ingress database system. That's why it's called Postgres. So Postgres has an active and vibrant open source community that continues to innovate in the core database product with new features and capabilities. And this is partially due to the type of open source license used by Postgres, which allows anyone to modify the source code however they want. In addition, Postgres is not owned or controlled by a single company. So it's owned by a nonprofit foundation, which addresses customer concerns about vendor lock-in. For features and functionality, Postgres offers really good performance out of the box, even before we start doing our Amazon Aurora improvements. It has transactional semantics, very similar to those of Oracle and SQL Server. It is object-oriented and ANSI SQL 2008 compatible, which makes it really easy for customers to migrate applications from other relational database platforms. It also has very strong support for geospatial capabilities with PostGIS. And it also supports stored procedures in many languages, including PLPG SQL, which is very similar to Oracle's PL/SQL. This combination of features and capabilities makes Postgres the most Oracle-compatible open-source database. And we even see that with our own AWS Schema conversion tool. That tool shows the highest automatic conversion rates are from Oracle R to Postgres. So it shows roughly a 60 to 70% automatic conversion rate on average for customer databases when they're trying to migrate from Oracle to Postgres. So what do we mean when we say we have made Amazon Aurora compatible with Postgres? Well, we started with the Postgres 9.6 code and have integrated Amazon Aurora's cloud-optimized storage into the lower layers. Amazon Aurora Storage maintains 6 copies of every write across 3 availability zones for high durability. It supports up to 15 read replicas with very low replica lag. It provides failover times of 30 seconds or less. And we are currently seeing performance greater than or equal to 2 times that of standard Postgres on standard benchmarks. Amazon Aurora Storage also includes cloud-native security and encryption, integrated with AWS Key Management Service and AWS Identity and Access Management. We've also integrated Aurora into Amazon RDS, making it easy to provision and manage. And customers can use AWS Database Migration Service and AWS Schema Conversion Tool to migrate data into the Postgres-compatible edition of Amazon Aurora, and also to migrate data out if needed. Now, it's important to keep in mind that we're running Postgres code. We're not emulating Postgres functionality with a compatibility layer. The Postgres-compatible edition of Amazon Aurora is a native Postgres implementation, and we plan to maintain full compatibility with Postgres for the foreseeable future. Now I'm going to hand it back to Mark, who will dive deeper into durability and availability with the Postgres-compatible edition of Amazon Aurora.
Thanks, Kevin. So I bet a lot of you believed a lot of that stuff because you're here. So now we're going to dive into how we did it and how it's important. So remember I told you about redesigning the relational databases from the ground up and ripping apart that stack. Well, you would want to take the bottom part of that stack and you'd want to have one that's distributed, one that copies data, one that has its own monitoring system, one that has spread across an entire AWS region, both so that you can run your applications in any place you want in that region and still get equal access to that storage system, and also so that in the event of some kind of failure, you're insulated from that, both at the application level and at the storage level. So we've already talked about some of this stuff. It's duplicated 6 times, but there's some stuff about this that's subtle as a database administrator or as a owner. One is that data is continually backed up to S3. There's no backup windows. There's no backup penalty. You're never going to be worried that your backup job is running at the same time as your payroll job. It just doesn't happen. It's always running. It has a separate monitoring and management infrastructure. And then it has something that we call a 4-6 quorum for writes. And this has both durability implications and it has performance implications I'll get into later. What does that mean? It means that when that database node writes 6 times to the different places, it actually goes and tells the database that it's done when it gets the 4th acknowledgement back from whichever one it comes back from. Well, now, what does that mean? Because what happened to the other 2? Well, the other 2 are probably just late. And what that means is that networks and disks and nodes, they can all stutter sometimes. Well, Amazon Aurora is jitter independent for those 5th and 6th writes. Not only that, because the system doesn't depend on those 5th and 6th writes, you can actually pull, as a management operation, pull any one of those 6 storage nodes out of the system and put it back in, replace it with a new one, do something different, upgrade it, and the system just keeps running. Now, there's something subtle when I talk to customers here, is they keep asking, well, what impact does all this have on the database? And I'll say it again and again through the presentation, none. The database keeps running, and I'll even say something else, you don't even know what's happening. There's no alert to you, there's no management console that shows you that the storage system is doing all this stuff. You know why? Because you don't. You don't know that the power company is putting more coal in the boilers, and you don't know that the storage system is repairing itself all the time. So let's go a little bit deeper on fault tolerance, because it's non-intuitive to a lot of people. What can fail? Segments can fail, 10 gig segments, those are disks. Nodes can fail, that's the middle red X's. And AZs, availability zones, can probably not fail. We've never had one fail, and we don't intend to. But sometimes the network connectivity to an availability zone can stutter or become impaired. So Amazon Aurora rides through all of those failures. In fact, you will be able to write as long as 4 of those are available, and you will be able to read as long as 3 of them are available. And that's pretty cool. Not only that, when something bad does happen, the database node doesn't have to get involved in fixing it. Those arrows between the storage nodes are the storage system actually fixing itself without talking to the database, without getting the administrator involved. It'll replicate all the missing segments all by itself. So another thing this gives us is great replicas. So everyone knows about read replicas. They let you scale out your read traffic. They let you do read balancing. But there's also this concept of durability and availability. And so again, at this layer, there's a completely hidden, independent database and instance monitoring service. Now this one will tell you what it's doing. When your instances fail over, you can get alerts on the console, just like your RDS databases. In Aurora, there's one primary writable node, as you can see on the picture, and there's up to 15 read-only replicas. And the system detects failing database nodes and replaces them, or fails over. And the system detects failing database processes and restarts them, all without you getting involved. In fact, in Postgres, the port number is 5432 that you connect to. And we like to think of our job as 5432 should always respond. That's it. That's the contract you make with us. And we want to do everything in our power to keep 5432 responding. So let's talk a little bit about that continuous backup. Because for those of you who run databases, you're probably always aware and you're running your backup scripts and you're wondering how it worked. Even with Amazon RDS, people track their backups. Well, with Aurora, you don't have to, because it's always taking snapshots. It's always taking log records out. And then when it goes to restore, all it has to do is bring back the latest snapshot of each segment and bring back the log records and apply up to whatever particular time that dashed vertical line is at, which is another power I'll talk about here in a little bit. But the key thing about this, which is different than databases you're used to, is that a typical Aurora storage cluster is hundreds of nodes. And this is in production all over the world today. And so when you think about how long it takes to bring back one of your databases, imagine how much faster it would be if you were bringing it back across 400 or 500 big, powerful 32 CPU machines with 10 gig each. Not only that, but Amazon Aurora has instant crash recovery. Now, instant, that's quite the word, isn't it? Well, the reason that's quite the word is because it actually doesn't have to do almost anything for crash recovery. Most databases write data blocks as you modify them, and then occasionally the database does what's called a checkpoint. And a checkpoint is it gets all the dirty data blocks up to a certain point out of cache, and then makes sure all the redo is out of cache as well. That way you know you can recover your database. Well, in Aurora, there's no database block written, ever. The node will never write a database block. It only writes log records. Well, so that means that the concept of recovery, where you have to read in database blocks, goes away. So the transaction system, the way you recover, is it comes up and it determines the last durable transaction written, and it says, hey, there you are. That's where you are. There's no recovery. Now, sometimes hardware's not perfect. Switches fail, CPU boards fry, weird things happen with racks, etc. When that happens, there's clearly no option to restart the database, so even Amazon Aurora can't perform magic in that case, because the database node isn't there anymore. So in the case of such a failure, you need to promote another database to the master, and this is called failover. So promotion of a read-only node to be the writable node is called failover. In Amazon RDS for Postgres, with our multi-AZ solution, we actually do pretty well. We detect the failure in 15 to 20 seconds. We start DNS propagation and recovery at the same time. And we get the node available. Typically, our P99 is around 68 seconds. Now in Aurora, we've actually done some stuff to optimize the failure detection because we own all the code in the database. And we've also done it so that recovery, I've told you, is really short. So now that doesn't go out past DNS propagation. And if you use one of our client drivers, which actually knows what the cluster is, it knows where the master is, and it knows where all the read replicas are, it can fail over like that. In fact, in Amazon Aurora today, we see failover times sometimes as short as 5 seconds. Now, that's not what you get all the time. We typically get 30 seconds. Now, you can imagine that we're going to be working hard to make that number lower. But this is just a game changer, because how would you like your databases to fail over in the time your users go, God, what's going on? It's back. They don't know the database failed over. You do. You got a page for it, just so you know that something happened. So now what we're going to do is we're going to talk about performance. And we're going to do it in 2 phases. The first is Kevin's going to tell you about the performance, and then I'm going to come back up and tell you how we did it.
Great. Thanks, Mark. Excited to dive in on some of the performance benchmark results. From the beginning, one of our major goals for the Postgres-compatible edition of Aurora has been to deliver much better performance for customers with demanding workloads. So as part of our performance effort, we of course run various standard benchmarks to compare how we're doing relative to standard Postgres. And so in the next few slides, I'm going to review a bunch of different results with different types of tests. And all of the tests were done with the database engine running on an M4.16x large, with the clients running on a C4.8x large, and both the database and the client nodes were in the same availability zone. For the Postgres tests, we used version 9.6.1, and we used 3 provisioned IOPS volumes of 3,000 gig each for a total of 45,000 IOPS. We created an ext4 file system striped across a logical volume on top of that storage, and we also enabled full page writes, checksums, and wall compression. This combination gives the best performance for Postgres while most directly comparing with the durability and availability built into Amazon Aurora storage. So let's first look at some PGBench results. For those of you who aren't familiar, PGBench is the standard benchmark that's part of the Postgres distribution. And it has several built-in modes. One of those modes is TPCB-like, in which PGBench runs transactions that are very similar to the standard TPCB benchmark. We ran PGBench in TPCB-like mode while increasing the number of concurrent client connections from 256 up to 1,536. We used a 30 gig scale 2000 size database, and we ran each test for 60 minutes. As you can see in the graph, Postgres reaches a peak of just under 18,000 transactions per second at 512 concurrent connections, whereas Amazon Aurora continues to scale up as more connections are added, reaching a peak of just over 38,000 transactions per second at 1,024 connections. The peak-to-peak comparison shows that Amazon Aurora delivers more than 2 times the throughput of Postgres, and the direct comparison of Amazon Aurora's peak with the corresponding Postgres result with 1,024 connections shows a ratio of greater than 2.5 times. So in this test, we use systbench, a benchmark utility often used to compare different database engines. We ran the systbench write-only benchmark, again while increasing the number of client connections with a 30 gig database. Postgres writes per second scale up until they reach just over 47,000 writes per second at 1,024 connections. Then the throughput drops as more connections are added. And you can see Amazon Aurora scales up to just over 92,000 writes per second at 1,536 connections, about 2 times more throughput when comparing peak to peak. Compared directly with the Postgres throughput at 1,536 connections, the ratio is more than 2.5 times. Another metric we track closely in our benchmarking is writes per second with systbench. And in this screenshot, you can see the results of a systbench run with an average of more than 120,000 writes per second. You'll also notice the reads were 0. This is because this was a write-only configuration of systbench. So let's take a look at database load performance. With the PG benchmark, you first, of course, have to load the database. And we compared the time it takes to load, vacuum, and build indexes for a scale 10,000 or 150 gig PGBench database. And as you can see, Amazon Aurora can finish the PGBench initialization phase about 3 times faster than Postgres. And most of the performance difference in load times is due to the database-specific storage optimizations that are key to Amazon Aurora Storage, and Mark will dive deeper into those optimizations in a few minutes. It's important to measure throughput, as we've been showing you, but it's also important to measure response time at scale. So we looked at systbench response times with 1,024 concurrent connections. On the graph, you can see very different behavior for Amazon Aurora as compared with Postgres. The response times for Aurora are much steadier, with much less variation. More precisely, we measured the standard deviations of the 2 data sets, and Amazon Aurora is more than 10 times more consistent than Postgres. Also, the average response time is about 2.9 times lower. So Aurora delivers much faster response times with much less variability. Now, you might wonder what's going on with those Postgres numbers. You see these big spikes cycling through the time graph there. And what you see is the impact of database checkpoints, which Postgres does to ensure that dirty pages in memory are periodically written to storage, as Mark described earlier, to ensure recovery times aren't extended too long. And so, of course, during a checkpoint, Postgres does a bunch of extra writes, which slows down user transactions. And that's where that variability comes from. Each of those spikes is another Postgres checkpoint kicking in. Let's go back to PGBench to look at consistent performance based on throughput. In this graph, higher is better. We're showing you throughput over time while running PGBench, again, in TPC-B-like mode. Now, we ran each database at the optimal number of clients to deliver the max throughput for that database and plotted the variability in throughput over time. As you can see, Amazon Aurora was much more consistent, just like the response time graph, and delivered significantly higher throughput. Based on standard deviation, Aurora is about 3 times more consistent than Postgres in this test. In this test, we compared how each database scales in terms of throughput as the database size scales, using, again, the systbench write-only workload. And you can see with the 10 gig database, Aurora delivers about 1.5 times better throughput. With the 100 gig database, Aurora delivers about 3 times better throughput. Basically, its performance didn't drop off as much as Postgres did. However, we're not really all that happy with this result. We'd like to get to the point where Amazon Aurora doesn't show a significant drop-off at all as the database size grows. Now, in all the tests we've shown you, we've tried to tune Postgres to deliver the best possible performance results. But one key part of that tuning is to reduce the number of checkpoints that occur during the test runs. And you do that by increasing the duration between checkpoints. A consequence of that is that it increases recovery time if there's a database failure. This is because Postgres has to start from the last checkpoint, the last time it wrote all dirty pages from memory to storage, and roll forward through all the wall records written since that last checkpoint. The more wall to roll forward, or write-ahead log to roll forward, the longer recovery will take. With Aurora, there are no checkpoints. So recovery time is independent of checkpoints, and it's independent of how many transactions are being processed per second by the database. So as you can see in the graph, we increased the checkpoint time for Postgres, and as we did that, the overall throughput increased, but so did the recovery time. So at the best throughput level for Postgres, the recovery time for Aurora was 85 times faster than for Postgres. That's really quite a big difference if you're running a high throughput production system. And the last thing to highlight there, of course, is that recovery time for Aurora was 1.2 seconds on average in the test we ran. Obviously, a very fast recovery time. So to summarize what we've covered in the last few slides, we showed results from both PGBench and systbench, demonstrating throughput 2 times to 3 times that of Postgres. We showed data loading 3 times faster. We showed response time to be more than 2 times faster, and both response time and throughput to be much more consistent. We showed throughput at larger scale databases to be 3 times faster, and we showed recovery speed to be much, much faster due to the innovations in Amazon Aurora Storage. So the performance results we reviewed are impressive. I can tell you we're not done. And I briefly touched on how we're achieving those numbers, But I'm going to hand it back to Mark now so he can tell you in a lot more detail how we're delivering these results.
Thanks. So I want to point out that I'm the general manager of Amazon Aurora for Postgres and RDS Postgres. Postgres is a great product. Postgres is the fastest, most efficient, most durable open source database out there. We just want to make it better. So having all those little slides where the blue is so much lower or farther to the left actually kind of hurts my heart a little bit. At the same time, I'm okay having 2 children. So, sorry. So there's no magic to any of this, okay? You got to have the processor do less work. You have to do work more efficiently. You have to do fewer lock operations. You have to do fewer I/O operations, okay? You have to reduce the latency path. You have to use lock-free data structures. So let's really quickly look at child number 1, RDS Postgres. So first off, RDS Postgres runs as a synchronous replica. It has 1 primary and a synchronous standby. 4 copies of the data are stored using Amazon EBS. And it's stored in 2 availability zones for reliability. And this works great, actually. And I'm proud to say that even though this is child number 1, this is the largest fleet of Postgres databases in the world by like an order of magnitude. And we're really, really proud to do this for our customers. However, this uses that same monolithic backbone that the other conventional databases use. Well, so how does it work in Amazon Aurora? Well, the first thing is we do things differently. Using that 4.6 quorum, remember I talked about that, we reduce I/O network jitter. In addition, we boxcar logged records, and that's a fancy word for sorting writes into buckets, which means that we actually do less I/Os, believe it or not, and smaller I/Os. In fact, in our studies, though in theory we're doing 6 times as many I/Os, right? Each write has to go to 6 nodes. In practice, by the time you put it boxcar together, with the fact that we're doing redo records and not data blocks, we're doing 9x less traffic. Now, when you're doing 9x less traffic, your network NIC is running at 11% what it used to run for the same transaction load. Now, I don't know what that says to you, but what it says to me is let's do more transactions. So one of the ways to do more transactions is to group them all together, to put them together to figure out what's going on. And this is actually pretty clever. The master database node is always keeping track of the furthest, most future transaction that has achieved durability. And we call that, because we're nerds, volume durable logical sequence number, or durable LSN. Now, the storage system underneath the database is independently managing all of these I/Os. And in one of these systems that's running 100,000 I/Os a second, it might have 5,000 or 10,000 transactions all hanging out at one time. And it's managing all of the writes for each of those. So what it does is as it's keeping track of those, as these batches come back, it can advance the durable LSN in big batches. And that's really efficient. It can complete lots of transactions. And so this batching, both from the database into the top of the storage system and from the main database node out to the storage nodes, is one of the main ways that Amazon Aurora scales. Now, because we're a really technical audience, let's dive down into one of the storage nodes. If you take nothing else away from this really busy slide, take away the fact that when the database wishes to commit a transaction, the only thing it has to wait for is items 1 and 2, which is it gets a batch of log records, it persists them to SSD really quickly, and it acts back to the database. Boom, that's it, we're done. Now, all the other stuff, which the bottom half of your database does today, and all the other stuff which your storage system does today, is all handled asynchronously by these storage nodes. And that includes organizing records, identifying gaps in the log, gossiping with peers, because heck, maybe I missed an I/O and I have to go get it from my peers. Coalescing those log records, because of course there are still data blocks, coalescing log records into data blocks. Well, that's just handled asynchronously in the background. Periodically staging all this into Amazon S3, and then also doing all sorts of cool stuff where you can garbage collect old versions and where you can run integrity checks. Well, I have an array of 400 or 500 nodes out there that can do all sorts of things in my database, which if I did them on my head node would slow down my transaction rate. And I don't want to do that. We also did some innovations specific to Postgres in Aurora Replicas. Now, on a typical Aurora instance, a typical Postgres instance, what happens is the redo, or wall file for you Postgres folks, is shipped from the master to the replica, written to disk, and then read back from disk and applied to blocks. Oh wait, those have to be read from disk and written to disk. There's all sorts of stuff going on there that doesn't need to happen. So when it applies it, if it's already not in memory, it has to go read the block. Well, so now Aurora, the blocks are shipped, the redo records are shipped across the network, no disk involved at all. They're applied to the cached pages, and they don't need to be written out. Again, the trick to be faster is to do less. It's not actually to be more clever. And again, I'm going to hark back to that Oracle RAC analogy I made earlier on. The theory behind Oracle RAC is we're going to be the cleverest people on the planet. The theory behind Amazon software is typically we're going to be the simplest people on the planet. So here's another realization that actually came about halfway through the Aurora project, which was that when you have a database instance, it has a shared buffer cache attached to it where all the blocks that are being held come in. And when that database process crashes, you get what is known as the dreaded brownout. And the brownout is where your application, your database process restarts, it does its recovery, however fast it does, but your cache is cold. Now let's take a typical machine like an R3.8 XL on Amazon. That has 200 gig of cache typically is how you'd run it. Your transactions were running with that cache full and hot. Well, now all of those transactions are actually hitting pages that aren't in cache. And even if you can read those back in at 1 gigabyte per second, and by the way, with random IOs, the chances of that are pretty low. But if you can even read them back in at 1 gigabyte per second, your database is experiencing severe degradation for over 3 minutes. So what we did was we took that buffer cache and we put it outside of the process, so the database process crashes, starts up, and reconnects to the buffer cache. Now, those of you who are programmers in the audience are sitting there going, no, that doesn't work, that doesn't work. Because that database process, when it was running, actually had a lot of data structures in that shared memory that it was modifying when it crashed. So right when we come back up, we go through and we check and verify all those data structures. Any data structures which do not pass our tests, we discard. Any data structures which do, we move. This test typically runs in under a second. Now, the one thing that does get thrown out is blocks that were literally in the process of being modified by code. You know, they were in an add instruction. That's typically less than 1% of your cache. So within a second or two, you have 99% hotness in your cache. Now there's a new feature which is being launched into Amazon Aurora, which is called database cloning. And this came along, it's brand new. It came along when we started realizing what it means to have a storage system like this, which is, I got all these blocks out there and I got this big distributed system. Wouldn't it be nice to just be able to get a version of that database that's, the current database and get it in a second? What if it's a 6 terabyte database? How long does it take you to restore a 6 terabyte snapshot? I bet it's longer than a second. So what we do is we just take a very quick picture of the metadata of what those blocks are at and what versions they're at. And cloning, in this first instant after you ran the clone command, just says, hey, the source database and the clone database both have blocks 1 through 4. And then what happens is as you take writes, and it notices, for example, page 2 in the first database, and I think it's page 6 in the second database maybe, those are ones where it's just writing to the second one. And it sits there and does what's called copy on write. Now, over time, of course, these things are going to diverge, but a lot of time when you're doing dev test or you want to stand up something on your own, then you don't really care how long it takes. Over time, you just care how long it takes to get started. The system also offers you another capability, something that we call online point-in-time restore. Now, we all know that database systems are reliable and nodes are reliable and all that, but you know what's not that reliable? Humans. Humans will often accidentally forget a where clause on a delete. Humans will accidentally update all your employee numbers to prime numbers. Humans will do bad things. Well, unfortunately, while they were doing that, all your other tables took transactions like credit card transactions that you don't want to lose and you got to figure out. So you do what you can do to get your data out, and then you want to roll your database back to a certain point. Well, remember how the storage system is transaction aware? You can literally tell one of those storage nodes, those green boxes, hey, can you please start giving me blocks as of this LSN, the one that's from 2:31 p.m. and 12 seconds. And then you can notice, when you look at that, oh, wow, no, that was wrong. We actually made 3 mistakes because that application program went crazy. Let's roll it back to 2:21 p.m. and 45 seconds, something like that, doesn't matter. And you can rewind multiple times until you get the exact point where you've preserved as many of the transactions you can, and yet you've overcome the human error. So now what I'd like to do is tell you a little bit about this new feature that we're adding to RDS called Performance Insights. And we know that looking into your database instance is important, and we want to do more of it. So I'd like to introduce Jeremiah Wilton, who's right here. And Jeremiah has been writing code for databases since 1993, and he has a very distinguishing characteristic, which is he was the first DBA for Amazon.com retail in 1997. And he lived. See, he's still there. He then went and did database consulting at his own company. And for those of you who are Oracle aficionados, he named his company Aura 600 Consulting. And then he did a stint at Blue Gecko, and now he's a principal engineer in the Amazon RDS team. We're thrilled to have him back. He's focused almost completely on this new feature, Performance Insights.
Thanks, Mark. So, along with this great new addition of Aurora with Postgres compatibility, we're really excited about this feature that we're launching alongside it. It's a new feature of the RDS platform, and what we're going to try to provide is an intuitive way to tune database workloads, even if you're not really a database tuning expert or a tuning guru. We've heard from lots of customers over the years that we've been running RDS that they really like a lot of things about RDS, the automation, the backups, the upgrades, the HA, the DR, the point-in-time recovery, and all that sort of stuff. But they'd like us to fill one gap that's been open for some number of years, and that's the ability to provide intuitive and guided tuning. And so we understood to try to fill that gap, a lot of the customers that would be using it wouldn't be expert DBAs or tuning experts. So we decided that we would try to design an approach to doing this that would be fairly intuitive with a single dashboard view that would naturally expose performance problems happening in the database. We started this some number of months ago. Over the past year, we've been improving visibility into RDS across all of the engines. And we started doing that with a new feature called Enhanced Monitoring this year. This feature provides detailed metrics from the underlying OS, from the operating system. It gives you the kind of data that you're used to getting if you're familiar with working at the command line with Linux tools like vmstat and iostat. And in addition to that, Enhanced Monitoring includes another kind of nice feature, which is a process and thread list. And with that, we're able to display for you on the console something very similar to the Linux top command, which lets you see which database processes are consuming the most CPU and the most memory. But OS stats are not enough for tuning databases. So Performance Insights is the next step. And it goes beyond operating system metrics and dives deep into the database engine itself. And in order to show you a little bit about what we've done, I'm going to do a live demo. Oh, okay, that looks pretty good. Let's see here. So let's look at how Performance Insights helps customers find the root causes of problems. As you expect from something that shows you information about database tuning, we show you the database engine metrics that you're accustomed to getting with third-party database tuning tools and things like that. So up here on this top graph, it shows these kind of traditional tuning metrics that you see with most tuning tools, the things that count up stuff that happens in the database, numbers of reads, numbers of writes, numbers of connections, amount of CPU used, things like that. In this top graph, you can choose which metrics you want to display. Each of the database engines in RDS have hundreds of counter metrics that are available in them. And Postgres is the same, and so is Aurora with Postgres compatibility. So that's sort of like the first part of Performance Insights. But we've decided that we'd like to innovate beyond those traditional metrics to provide better guided discovery of performance problems. Performance Insights centers around a new core metric called database load. It's a metric that makes performance bottlenecks stand out. And it's meant to help guide users to the root causes of problems. So database load is in this middle graph, and it's front and center in this in Performance Insights. You can see by looking at this, sort of how graphing this metric tells you how saturated the database is. You can see that at this time, the database is more saturated than it is at this time, or at this time, during the time frame that's displayed. So the other cool thing about it is because we've sliced this by the different kinds of ways that load is being expended in the database, you can see what's responsible for most of the load in the database by looking at the different colors that that graph of load is made up of. In this example that we're looking at right now, you can see that we're looking at a database that is somewhat heavily loaded compared to the number of vCPUs that are available. You can see that we have a horizontal line across the graph that shows you the number of vCPUs on the instance. In this case, it's about 4, I think. And you can see that when you look at the database load, which is really actually a metric that measures concurrency at its heart, you can see that the degree of concurrency at certain points in time is greater than the number of vCPUs on the instance. It doesn't necessarily mean that you've saturated the CPU on the instance, but it does tell you something useful, which is that you are running with more sessions and more users active in the database at that moment than you have vCPUs. In this new UI, we have the ability to zoom in to the 5-minute level, which is what we're looking at right now. But you can actually zoom out to a variety of levels, up to 35 days, which is the retention period for the performance data. So we zoomed out to 1 hour just now, to the 60 minutes. So you can see a nice history of how workload has been transpiring on this database. By default, in this middle graph here, we see the database load broken down by wait event. What that does is tell you the type of activity that's consuming the load. But you can also choose to break down that load by any of a variety of other dimensions. Besides wait event, you can break it down by SQL statement, and that tells you which SQL statements are dominating the load. You can break it down by hosts that are connecting to the database, the client machines connecting to the database, and that tells you which client machine is dominating the load. Or you can break it down by users. You can see which user is responsible for most of the load. Now, going back to weights, below the load chart, below this database load chart, you can see a list of the top SQL statements. And that's ordered by, again, our core central metric in Performance Insights, which is database load. In this list, you can see which SQL is most responsible for the load in the database and which type of activity is causing each one of those SQL statements to consume load. If you look at this, it's kind of interesting. So if you look up here, here's the legend of colors, and you can see that blue represents CPU. If you go down here and look at the SQL statements, you might wonder to yourself, who's using all that CPU? Who's responsible for all that blue in our load graph? Well, it's pretty easy to pick out who it is. It's this one select foo paren here. Well, it turns out I did that so that I could demonstrate a session heavily consuming CPU. That's a function that I wrote in Postgres. And by the way, this is connected directly to an Aurora cluster, which is Postgres compatibility. So yeah, the function is just in an infinite loop calculating the square root of a random number, which tends to run the CPU up. So you can see that there. So this is to help guide you towards finding which SQL statements are responsible for exerting certain types of load on your database. It's hard to miss that when you're looking at weights as a dimension here, there's a big orange, and if you look at orange up here on the legend, it says unknown, which is a little bit sad to look at when you're looking at a tuning tool. And the reason that that's there is because right now the PostgreSQL-Compatible kernel is not yet 100% instrumented with wait events. As we add instrumentation to this system, the amount of that unknown time will eventually reach 0, and we'll be able to, in this tool, account for all of the load that occurs in an Aurora database, so that when you look at this tool, you'll be able to identify exactly what types of functions are responsible for all of the load across your entire workload in the database. You might also have noticed that some of the SQL statements down here below have question marks next to them in the where clause. instead of real values. And that's because what we do is normalize large numbers of very similar SQL statements, the kind of SQL statement that only varies by the where clause, like where ID equals value. And we're normalizing all of those hundreds and hundreds of different versions of very similar SQL up into a single logical SQL called a digest. And the reason we do that is so that we can show you the real impact of that SQL in total on this screen. So if you want to know what the SQLs that are actually comprising each one of those digests look like, you can actually just drill down into it. And you can see here's the parent, and here are all the children. Now in this case, all the children are using just about the same amount of load. So in total, they're more or less appear to be contributing equally to the parent. But it might be that when you opened that SQL up, you'd actually see that maybe one or two different types of permutations of that SQL might be the more expensive ones. And then that would lead you down the path of going and paying attention to that particular SQL statement that uses those predicates rather than the SQL statements that don't use those predicates. So again, this tool is designed to help guide you to the root cause in a really quick and effective way. Again, even if you're not a tuning guru. So once you've selected one digest, there's one other kind of interesting thing to notice about the UI. Have you noticed how the load graph has changed now that we've selected one of the SQL digests? The load graph now shows only what that one SQL digest contributes to the database load overall. So you can see now that we've selected that one SQL digest and drilled into it, the view of the database load now is now colored only in the areas representing the load that SQL represents. We have flyover, so you can move your cursor over and see exactly what values are occurring at any given time in all of the different metrics. So that's a sort of a quick tour of performance insights. Unfortunately, we don't have time to drill into a whole lot more of the capabilities. But I'll tell you one or two other things about it before I finish up. So Performance Insights has a lot of other great features besides the ones I just got to show you now. Other things that it has are lock detection, to be able to determine who is blocking and who is waiting for locks and who is the ultimate holder of that lock chain and what they're doing at that time and why they're responsible for doing that thing. Execution plans, obviously when you drill down into those SQL statements, you're going to want to be able to see what execution plans those are running. And this whole thing is API based. This console is doing nothing but calling the public API to Performance Insights. And what that means is that you can develop software that runs against this and build your own monitoring tools or your own alarming tools or anything that you want around the data that we're emitting via Performance Insights. This feature is included in RDS at no additional charge. By default, it includes 35 days of performance data retention. And right now, we're making it available initially on the PostgreSQL-Compatible edition of Aurora, but you can expect it to cover the remaining RDS databases in our suite over the course of the year of 2017. So if you are participating in the preview of the PostgreSQL-Compatible edition of Aurora, make sure you ask your TAM or your AWS representative to request to also be whitelisted for the preview of Performance Insights. And if you don't have a direct contact in AWS that you work with day in, day out, we'll be providing you a way to sign up for that preview online on the console for Aurora as well. So that's about it for Performance Insights. I'm going to hand control back to Mark.
Jeremiah and I have been talking about that feature for quite some time, and I'm so excited to see it out there. And this is just the beginning of a multi-year thing we're going to be doing. So now I'm going to spend a couple seconds reviewing our roadmap, and I'd really like to get to questions and help you out. So the things which we have on our roadmap at launch, which is going to be in the first half of next year, this is preview we're going into right now. You know, I want to highlight, it is 2x or faster on Postgres on most workloads. There are certainly workloads it's going to be exactly the same on, such as in-memory cached workloads where it's just the Postgres code working. But most workloads that involve I/O, it'll be significantly faster. It has all Postgres features. We already said that it's native. It has all RDS for Postgres extensions. A lot of you are going to come up afterwards and say, does it have extension X? And I'm going to say, wait, is that in RDS Postgres? It has AWS DMS supported inbound replication. Now, it's going to eventually have DMS outbound, and we'll launch that as soon as we can. It'll have up to 15 readable failover targets. It'll have that instant crash recovery. In fact, it'd be hard for me to offer the feature without it. And it's going to have security built in from the ground up. Now, there's other things on the slide we can talk about, but those are the main features. So, when we think about Amazon Aurora, we think that it's secure with encryption at rest and in transit, IAM, KMS, all that stuff you've gotten used to. It's durable. It has 6 copies at runtime with a copy going all the time to S3, 11 nines. It's available with automatic failover and read replicas. It's convenient to load up with DMS or PG dump. It's convenient to use with Amazon RDS. Click on the console. When you get the preview, it's one click to go create one. It's now compatible with 2 things, which is even more fun. And it has enterprise-class performance and enterprise-class storage. So now, we're taking signups for the preview now. That URL on the page is not the world's most complicated URL to go sign up. Just sign up for RDS/Aurora or even aws.amazon.com/Aurora. There's an FAQ already put up there where you can get some questions answered. And then there's these email addresses at the bottom, which I would like and expect you to use. We are very passionate about this product, and we would like to help you out. So thank you so very much. Remember to complete your evaluations. And thank you.